Thanks very much, and thanks for having me here. So, as you mentioned, I'm going to talk about why it is we get the same forcing for each doubling of CO2 concentration. And what I'm showing here is the apparatus that John Tyndall had set up to measure the absorption spectrum of CO2, which is a little bit of a hint that that might have something to do with the answer to the question. But that is getting a bit ahead of myself. So the next three slides are going to be the most boring slides in the entire talk. So if you get through these without falling asleep, then it bodes well. So first I want to tell you, if I can indeed advance the slides, which I can, that I want to tell you what tools are used in this work. Very briefly, one of them is Das Atmosphärische Model, or DAM, which is a cloud resolving model. Another is RRTMG, which is a correlated K radiative transfer model. Then the reference forward model by Anno Dudia, which is a line-by-line radiative transfer model. And finally, there's a lot of pencil and paper, which I have to credit the Chinese with. So these are the tools that are used in the work I'm going to show you here. And this work is described in a paper that's currently in press with the Journal of Climate that I wrote with the Jakes. That's Jake Seeley, who's a postdoctoral fellow at Harvard, and Jake Edman, who's a senior scientist at Cobalt Metals. So this paper has a lot of the details in it, actually in a way an excruciating level of detail. I am not going to go through all of that detail in this talk. So in a way, I'm not going to prove all of the steps along the way and show you that all the pieces fit exactly. If you're really interested in digging through all of those details, you can go look at this paper. And as I mentioned, it's detailed. It has some 20 figures in it, and which is a lot by my count. And it's the first time I've ever written a paper with 20 figures. In a way, I hope it's the last. So it's very detailed. But if you really wanted to dig into the details, you can. They're in this paper. You can get it from my website. In the more likely, at least in a relative sense, that there's someone who just wants to get a refresher on what it is I talked about in this seminar, then you can go to section 3 of the paper. So skip sections 1 and 2, skip sections 4 through 50, or whatever the number is, and just go to 3, and it will explain to you what the basic mechanism is, give you some of the equations that we talk about in this seminar. And I should also tell you that the idea here that we're talking about in this paper is not something that we've came up with first. It's not original to us. This is an idea that's been in the literature before. It's just that our paper goes through in far more detail than other papers have as to why exactly this works, and including effects like pressure broadening, etc. To the best of my knowledge, it was Ray who first published this explanation in some writings around early 2010 or so. Okay, so I also have to give you a definition. I'm going to be talking about total forcing quite a bit in this talk, and sometimes I'll just say forcing, and I apologize when I do that. But what I mean by forcing usually, or total forcing, is the net outgoing flux to space or through the tropopause without the greenhouse gas minus the net outgoing flux with the greenhouse gas at some particular concentration. So that's the total forcing. If you want to know the forcing from, say, a doubling of the greenhouse gas, you need to take the total forcing at, say, 2 times Q, where Q is the concentration, minus the total forcing at just Q. So it's the difference between the total forcings that would give you that forcing from a doubling. Okay, so total forcing again is net outgoing without the greenhouse gas minus net outgoing with the greenhouse gas at the concentration that you have. Okay, with that definition in hand, we then go look at the total instantaneous forcing from carbon dioxide as a function of the carbon dioxide concentration. And this is for a particular snapshot of that cloud resolving model chosen because it's got lots of nice complication with relative humidity distributions and clouds, etc. And what you see is we've got on the x-axis about the carbon dioxide concentration, and it's a log axis. And the concentration spans here from 4 to about 4,000 parts per million by volume, so 3 orders of magnitude. And the y-axis is the total forcing. Again, net outgoing without the greenhouse gas minus net outgoing with this concentration. And you see that the total forcing is linear, or approximately linear, in the log of the concentration. This is what we refer to as log scaling. Now, in the title, I talked about getting the same forcing for every doubling of CO2, but that's really an equivalent statement. If I say that we get the same forcing for every doubling of concentration, that's the same as saying that the total forcing is linear in the log of the concentration. And you can see that here because each circle on this plot is for a different factor of 2 concentration. The vertical distance between the dots is the forcing you get from a doubling, and it's the fact that the total forcing is linear in log of concentration that tells you that the distance, vertical distance between the dots is fairly constant over this range of concentrations. So that's the equivalence between the statement we're trying to explore from the title of the talk and the total forcing being linear in log of the concentration. Okay, so if we go to the cloud resolving model, this is an animation of one of DAM's simulations, and we just take a snapshot from it and then perform some radiative transfer calculations, we can begin to see what components of the atmosphere are really essential for giving us this log scaling. So we'll take a snapshot of this and just plot up the all-sky total forcing at the tropopause. And you get, as I showed before, this curve that's roughly linear in the log of the concentration. But what aspects of the atmosphere are really important for this? Do the clouds matter? Does the distribution of water vapor matter? Well, we can start to strip away these things to find out what is truly essential. So if we look, again, all sky, but now we look at top of the atmosphere as opposed to the tropopause. So now we're looking at the total flux emitted to space as opposed to the net flux at the tropopause. Again, we see a total forcing defined in this way at the top of the atmosphere that is still linear in the log of concentration. Okay, so it's not anything special to do with the tropopause. If we strip away the clouds, so we make the clouds transparent to long-wave radiation, again, the total forcing is linear in the log of concentration. So it's not anything having to do with clouds. And if we even make water vapor transparent to long-wave radiation, so that carbon dioxide is the only radiatively interactive substance in the atmosphere. So this is what I call here dry sky. Then again, we still get this logarithmic behavior. The total forcing is linear in the log of the forcing. So now we know what things are not essential to the story. And so we'll henceforth focus on thinking about an atmosphere that is completely transparent to long wave, except for the presence of a single well-mixed greenhouse gas. And of course, our focus will be primarily on that greenhouse gas being carbon dioxide. Okay, so moving on then with this exploration of what causes this behavior in a dry atmosphere, the single well-mixed greenhouse gas. Now, in the abstract for this talk, I said that the one prerequisite for understanding this talk was knowing what optical depth is. But that was before I had actually made the talk. So I made the talk and decided, oh, well, I'll just explain to people what optical depth is. I understand the vast majority of people listening already know and know full well. So those folks can go to sleep now, and I'll clap or something to wake you up when it's time to pay attention again. So the optical thickness, which I'm going to write as d tau, of some slab of stuff is just the fractional area of absorption that that slab presents to light. So we can picture the slab like this. It's got this slab of, say, air or vacuum or whatever you want that has embedded within it absorbing spheres. So if I've got light that's traveling upward through the slab, it'll pass fine between the spheres, but it'll be absorbed by the spheres. In other words, the spheres will cast a shadow beyond the slab. So I can calculate what the d tau is. So again, the optical thickness d tau is the fractional area of absorption. So if I give some dimensions to this, we say the slab is 10 meters by 10 meters square, and let's say the absorbing spheres have a radius of 1 meter, then we can calculate what fraction of the slab is absorbing. It's simply the projected area of the spheres divided by the area of the slab. So the area of the slab is 10 meters by 10 meters, so it's 100 square meters. That's in the denominator. And in the numerator, we have the sum of the projected area of the spheres. Each sphere has a projected area of pi meters squared. So there are 4 of them. So it's 4 pi divided by 100, or pi divided by 25, or 0.13. So this is a simple classical example of a optical thickness for a slab with these absorbing spheres in it. By Kirchhoff's law, the area that's presented for absorption is also the area that's available for emission. So if d tau is the slab's fractional area of absorption, then d tau is also the slab's fractional area of emission. So to give you an analogy here, if we have just a solid black slab, solid, completely black, it will do the following two things. It will emit upwards an upwelling flux per area of pi times b, where b is the Planck distribution. This thing that's a function of temperature and wavelength tells you how much spectral radiation is emitted by that surface. So it's going to emit pi b. For radiation that's coming up from below, that's upwelling from below, the slab is going to absorb all of it, just a black slab. So this is what a solid black slab does. Now, a slab of air that has an optical thickness of d tau will do something very similar, except that it acts like a fraction d tau of an actual solid slab. So if I have this fraction of the slab of air here with optical thickness of d tau, it's going to emit an upwelling flux of pi b times d tau. It's just a fraction of the projected area that is covered by these black spheres. And for radiation coming up from below, it will absorb d tau of that radiation, again, because the projected fractional area of those black spheres is d tau. So if I just switch back and forth between these two slides, you see, okay, the emitted flux, pi b, got replaced by pi b times d tau. And instead of absorbing all of the upwelling flux, it's absorbing d tau of the upwelling flux. So that's what d tau is. Very simple thing. Now I can imagine taking these slabs and stacking them on top of each other. And for each slab, the locations of these black spheres are going to be random. They're going to be distributed randomly. And so if I am looking down to this column from above, that first slab is only covered maybe 10% by these black spheres. And the second layer is also going to be about 10% covered by black spheres. Mostly they won't overlap between those two slabs. So, but I can still, they're effectively transparent. I can mostly see through those first few slabs. So this column is mostly transparent in the beginning, but I have a hard time seeing down to say tau equals 2. So tau here, I should say, is just the integral of the d taus, or the sum of the d taus of these slabs. It starts at 0 at the top, then you add the d tau of the first slab, then d tau of the second one, and so on and so forth, to get tau as this measure of optical depth into this column. So I can see easily through small tau. I cannot see very well into large tau. What I can mostly see on average is black spheres at a depth of about tau equals 1. So if I'm thinking about long wave radiation, it's a level of about tau equals 1 that is predominantly emitting to space. And this is an important fact for us, because where it is you're emitting to space and the temperature of that location tells you about how much radiation you're throwing to space. This is very closely related to the forcing. In the atmosphere, we have a similar thing. We've got layers of the atmosphere. Instead of black spheres, we have CO2 molecules. The CO2 molecules are not like black spheres. They interact with radiation quantum mechanically, but for a given wave number, they act effectively like black spheres of a particular radius. And it's at the height in the atmosphere where tau equals 1 that's going to be mostly emitting to space. And it's the temperature of that tau equals 1 level that will tell us, via the Planck distribution, how much radiation per area per time is being sent to space. So it's the location of that tau equals 1 level that is so critical for understanding radiative forcing. Okay, now a bit of physics here. How do we write tau mathematically? If I'm at some level in the atmosphere, how do I calculate the tau where I am? Well, the tau where you are at some level in the atmosphere is proportional to the product of these four things. Q, the concentration of the greenhouse gas. Kappa, which is the absorption coefficient. It's a property of the greenhouse gas that tells you effectively how big those black spheres are. And then two factors of pressure. And I'll walk through these in turn. So again, I'm at some height in the atmosphere, and I want to know what my tau is. Well, clearly, the tau where I am will be linearly related to the, approximately linearly related to the amount of greenhouse gas that's above me. So we're thinking about a well-mixed greenhouse gas. So Q, the concentration, is the same everywhere. So the higher Q, higher the concentration of the greenhouse gas, the more overlying greenhouse gas there is, and so the higher my tau must be. That's simple. Kappa is this absorption coefficient, which I mean to be at a reference pressure and temperature here. And again, this tells us what the effective radius of these black spheres are in this analogy. It tells us how well the CO2 molecules are coupling to the radiation. So if kappa were 0, then the black spheres have 0 radius. The CO2 molecules aren't interacting with long-wave radiation at all, and so my tau is 0. The higher kappa is, the more absorptive the overlying air is, so the higher my tau where I am. And then there are these two factors of pressure. The first factor of pressure is very simple. We just think about hydrostatic balance. The pressure where I am tells me about the mass of overlying air. The more mass of overlying air, the more CO2 molecules there are, and so the higher the tau is where I am. And the second factor of pressure is a little more nuanced. It has to do with pressure broadening. And so the higher the pressure, the more molecules get to bounce around off of each other. And that actually, for most wave numbers, increases their efficacy of interacting with radiation. Not for all wave numbers, but for the vast majority of wave numbers, they're going to have their absorptivity or absorption scale linearly or roughly linearly with pressure. So we've got these four factors strung together to tell us what tau is. So tau at some height in the atmosphere is proportional to the concentration of the gas Q times the absorption coefficient kappa times pressure squared. So if we've got that piece of physics under our belt, we can do something with it. We can now define an emission pressure. Let's define the emission pressure as the pressure where tau equals 1. I mentioned before that tau equals 1 is really important because this is where most of the radiation is being sent to space. And it's the temperature of that location that's going to tell us how much radiation we're getting from that level. So the emission pressure is really important. So let's define the emission pressure as the pressure where tau equals 1. Okay, if we do that, then we can solve for the emission pressure. So 1, I just replace tau with 1 in that top equation. So now 1 is proportional to Q kappa emission pressure squared, or stated another way, Q times kappa times the square of the emission pressure is a constant. And this means that the emission pressure is proportional to Q, the concentration, times kappa, the absorption coefficient, to the minus 1/2 power. And from that, if I take the log, both sides, I get that the log of the emission pressure is linear in two things here. It's linear in minus log of concentration divided by 2, and also minus log of the absorption coefficient divided by 2. So this is really useful information. It tells us that every time we double the concentration of the greenhouse gas, the log of emission pressure will change by minus log of 2 over 2. I've put this in a box with highlighter yellow here to emphasize that this is important. We just did some really simple math. We first motivated that tau is proportional to Q times kappa times p squared, and then we just took the log basically and concluded that the emission pressure, the pressure at which you are predominantly emitting to space, will decrease by log of 2 divided by 2 every time you double the concentration of the greenhouse gas. So this should set off probably some little bells for you, because you remember the title of the talk is something like, why does the forcing from CO2, why do you get the same forcing for every doubling of the concentration. Here we see that every doubling of the concentration of a greenhouse gas is going to move the emission pressure, or the log of the emission pressure, by the same amount, by minus log of 2 divided by 2. So this then leads into the lapse rate explanation for why it is the forcing from CO2 is the same for every single doubling. And the explanation goes like this. So first, let's imagine that we can approximate the temperature profile as being linear in log of pressure. So I'm writing here T squiggle, which I'm using to represent a linear relationship. So T is linear in gamma times log of pressure. Here gamma is not with units of Kelvin per kilometer. It's just units of Kelvin because we're using this log pressure axis here. So the first question is, is this any good? Is it okay to say that temperature in the troposphere is linear in log of pressure? Well, we can go look at ERA5 and just average over the globe. And what I've got plotted here is temperature being linear on the x-axis, and I've got log of pressure on the y-axis. And the gray curve here is the average from ERA5. And the black line is just a linear fit. And you see that, yeah, to some approximation, the temperature profile in the troposphere on Earth is approximately linear in pressure. Certainly good enough for our purposes here. So great. So we're going to just put a green check mark here and say, yes, all right, to some semi-decent approximation, temperature is linear in log of pressure. Now, if you're okay with this, and I think you should be, then everything else follows almost immediately from what we learned on the previous slide. So if temperature is linear in gamma times log of pressure, it means that the emission temperature, so the temperature of the tau equals 1 level, is linear in gamma times log of the emission pressure. Just follows immediately from the preceding equation. And if we recall from the previous slide, we learned that if we double the concentration of the greenhouse gas, then the log of the emission pressure decreases by log of 2 divided by 2. Well, if I look at this equation, Tm, the emission temperature, is linear in gamma times log of the emission pressure, I now know what happens when I double the greenhouse gas concentration. The emission temperature changes by this simple factor, goes down by gamma log of 2 divided by 2. Now, for any smooth function, I can approximate it as linear in its argument, so long as we're looking at small changes, and this is also true for the Planck distribution. We can approximate the Planck distribution as being linear in the emission temperature. And so, or I should write proportionality there instead of linear, there's an unknown, there's a coefficient there. But anyway, so B is proportional to the emission temperature. And we see the emission temperature changes in this very simple way for every doubling. So the change in B is also just proportional to this gamma times log of 2 over 2. And the forcing from a doubling of CO2, which I'll denote here by F with a 2 times in the superscript, is just minus that. So the forcing from a doubling of CO2 is proportional to gamma, that lapse rate, times log of 2 divided by 2. Now, what's important to note here is that the thing on the right-hand side does not depend on the concentration. So it means that no matter what concentration you're beginning with, if you double the concentration, you will get this forcing. And you'll get the same forcing, regardless of what starting point you have. So every doubling of CO2 will give you the same additional forcing, the same addition to the total forcing. And so, success. We've explained why it is we get the same forcing for every doubling of CO2, or effectively why it is we get log scaling for the total forcing from carbon dioxide. But let's probe this just a little bit. Have we really succeeded? And I'll note that this explanation is found in textbooks, it's found in the peer-reviewed literature, but let's take a closer look. Remember, in this explanation, we haven't used any information about CO2. we use this general idea that tau is proportional to Q, it's proportional to kappa, it's proportional to pressure squared. These are generic statements. It wasn't specific to CO2. So we've used no information about carbon dioxide in this derivation. But that then begs the question, why don't all greenhouse gases then have this log scaling? Carbon dioxide certainly does. This is the empirical formula for the forcing from carbon dioxide. We use a log because that fits the data best. But if you look at methane, you've got this square root business. Same thing for nitrous oxide. The CFCs, they're linear in their concentration, certainly not logarithmic. So something's wrong. Our derivation that we just used, this lapse rate explanation, would seem to work for any greenhouse gas, at least theoretically, and yet it only seems to work for CO2. So let's be generous here. We see that the lapse rate explanation does not work in general, but maybe for some reason it works for carbon dioxide. So what could that reason be? Well, let's actually see if that's true. So here is, again, one of these plots from of the radiative forcing, the total forcing, in that cloud resolving model. And here I've got a simple setup. I've got a surface, I've got a troposphere with a fixed lapse rate, and then an isothermal stratosphere on top of that. And we get this log scaling. Now remember, the lapse rate theory depends critically on the existence of that lapse rate in the troposphere, because the forcing is proportional to the tropospheric lapse rate. The F2x, that's forcing from a doubling, is proportional to gamma. Now, if we get rid of the troposphere entirely, or we replace the troposphere with just an isothermal layer, the same temperature as the stratosphere, now gamma would be 0, and lapse rate theory should tell us that the total forcing is just constant, because you get no additional forcing by doubling CO2. Intuitively, the reason that would be is you move the emission pressure to lower values, higher in the atmosphere, but the temperature, the emission temperature, doesn't change at all if you're isothermal, and so you'd get no additional forcing. But if we actually remove the troposphere and just put this isothermal stratosphere directly in contact with the surface and recalculate the forcing from CO2, we get basically the same thing. We still get this log scaling. So this is completely contradictory to what the lapse rate explanation would lead us to believe. So we get log scaling even without a troposphere, and so the lapse rate explanation is wrong. Now, this is certainly a setback, and it feels like we're back to square one without having made any progress. But actually, we have made some progress because we've learned something about greenhouse gases, which is this notion of how emission pressures change for every doubling of concentration. That log of 2 divided by 2, that's still roughly right. But we did something wrong in the lapse rate explanation. So we didn't really think about the whole system. So why does the forcing from a doubling of concentration, why does that stay constant? We still need to answer that question. Well, to answer this question, we need to know something about the particulars of carbon dioxide itself. This is a busy plot here, but let me just step through it. In the x-axis here, I've got wave number, which is just the inverse of wavelength. And wave number here ranges from 0 to 2,000 inverse centimeters. In the top panel, I have plotted the kappa, the absorption coefficient at a reference pressure for carbon dioxide. And you'll see the y-axis there, it's a log axis, and kappa ranges over many orders of magnitude. It's phenomenal, actually. And so where you have the peaks of the mountains in this plot, those are the wave numbers where the CO2 molecules act effectively like really big black spheres. And in the valleys, those are the wave numbers where the CO2 molecules act like tiny black spheres, intercepting relatively little of the radiation. So this plot is telling us effectively about the size or the radius of those black spheres, and we see the radii range over orders of magnitude over this range of wave numbers. Now in the bottom panel, what I have is plotted two of the Planck distributions for two different temperatures. representative of a near surface temperature of 289 Kelvin, and a cold point tropopause temperature of 205 Kelvin, just for reference there. Now, this is where you have to just trust me, and I'll tell you that most of the forcing, the vast majority of the forcing from CO2 comes from the 15 micron band, which I've highlighted in gray here. And the reason for this is that in this band we have sufficiently large kappa, but not too large, but sufficiently large kappa. And also we have high values of the Planck distribution. This is where the Planck distribution would be sending out to space a lot of the radiation. CO2 has high enough kappa to interact with that and change things. So it's the 15 micron band that's doing generating most of the forcing. So I'm going to just zoom in on that 15 micron band here. I'm going to take these two panels, we're just zooming into the 15 micron band. That's all I've done. So 1 divided by 15 microns is 667 inverse centimeters. So it's right in the middle of this plot. And I've defined somewhat arbitrarily the 15 micron band as being from 467 inverse centimeters to 867 inverse centimeters. So, and I've also got the two Planck distributions plotted here. Now, I want us to note two things about the curves that are shown here. The first is that these two Planck distributions maintain more or less the same distance between them over this range of wave numbers. Which is to say, if you change the temperature from 289 to 205 Kelvin at 867 inverse centimeters, you'll get the same change in spectral flux as you would get at 467 inverse centimeters. So this is really valuable. It tells us that for the range of Earth-like temperatures, it doesn't really matter where we are in this wave number interval, we're going to get the same change in emitted flux for a change in temperature. And what that tells us is that the order of the actual wave numbers in this spectrum shown on the top doesn't really matter. I could rearrange them and I would have the same physics going on in the atmosphere because they're tied to the same changes in the Planck distribution. So if I look at this distribution of kappa, I can take that distribution and just reshuffle all of those values in order of increasing kappa. So basically I'm taking wave numbers and I'm reordering them to give a monotonically increasing kappa. And what you get when you do that is this dashed line here. And what's important to notice about this dashed line is that it is very approximately linear in wave number. There are deviations for sure, but to a good approximation, it's linear. So again, what I've done is I've reordered the wave numbers in order of increasing kappa. In a way, this is telling us about a cumulative distribution of kappa over this 15 micron band. So with these two things that we've noted, we can greatly simplify the spectrum of CO2 and the Planck distribution as well. We can replace what looks like something complicated on the left-hand side and replace with our simplified version on the right-hand side, where I've made the Planck distribution independent of wave number, because for forcing, all that really matters is differences with temperature. And as we saw, that difference in temperature with temperature is the same for the different wave numbers. And then we've taken the kappa, the complicated looking kappa that we have on the left, and we just sorted it and approximated it by this line. So this is our simplified system that allows us to understand the forcing from CO2. If I look at this kappa, what we see is that for each interval, each equal sized interval of wave numbers, I have the same sized interval of log kappa that corresponds to that set of wave numbers. So what this tells us is that the wave numbers in the 15 micron band, whether I resort them or not, are distributed uniformly on an interval of log kappa, an interval that you can see by looking at the y-axis here. So if I take the wave numbers in the 15 micron band and I just plot a distribution function of these on log kappa, what you would see is that you have approximately this uniform distribution on an interval of log kappa, log of the absorption coefficient. Now, we learned before that log of emission pressure is linear in log of kappa. So if the wave numbers are distributed uniformly on log kappa, they'll also be distributed uniformly on log of emission pressure. And this is a really important fact that allows us to give an intuitive explanation for why the forcing from CO2 acts the way it does. Okay, so that was a lot. And if I lost you, now's the time to come back, and I'm going to get you back on board the train here with a actual train analogy. Okay, so yeah, this is where we're going to put all the pieces together. So I've got here the surface with then a troposphere overlying it, and then a stratosphere on top of that. And I have a railroad track here that's moving along the surface and then starts to ascend up through the atmosphere. From the things that we've learned, we can think about CO2, the 15 micron band of CO2, as a train. So in this analogy, each train car represents an equal size set of wave numbers, that share similar kappa. So each car is a set of wave numbers, an equal size set of wave numbers, and we're going to be able to visualize CO2's emission to space using this train that's ascending this track up into the atmosphere. Now the way this works is each car, which again is a set of wave numbers, is emitting directly to space from where it is. So the location of the car corresponds to the tau equals 1 level for that set of wave numbers. And the temperature at that tau equals 1 level in the atmosphere tells you how much spectral flux those wave numbers are sending to space. So again, they're sending directly to space because that's the definition of tau equals 1. The height of the car in the atmosphere tells you where the tau equals 1 is for that bunch of wave numbers. If we have wave numbers that have really low kappa, then the atmosphere is effectively transparent, and so the surface at those wave numbers is going to emit directly to space. And so those train cars with wave numbers with really low kappa, they're sitting on the track on the surface here. And it's warm there, it's 289 Kelvin. So they're sending a high amount of spectral flux to space, represented by this wide spotlight that each car is sending to space. But a car that's up high in the stratosphere, well, it's cold up there. So its tau equals 1 level is cold, and so it's sending a small spectral flux to space. So this is the picture of the emission to space from CO2. And let me now remind you why it is this train analogy is so apt. So the fact that we can think about this as a train of train cars that are linked up one after another has to do with a simple spectrum of CO2 in its 15 micron band. We saw that we could approximate the 15 micron band by this very simple kappa that's just exponential in wave number. In other words, for every, the wave numbers are uniformly distributed on log of kappa. And this is what arranges the train cars one after another. If we had reordered the wave numbers and gotten still a monotonic kappa, which we would have to get by construction, but one that's not linear, instead looks something like this, then the train analogy would break. Because instead of car after car after car all linked up normally, we would get some mess that looks like this. We'd get a break in the train. Or we'd have train cars that are side by side instead of one in front of the other. And this is not a train. No train in the world looks like this. Now also, we learned in the very beginning part of this seminar that every doubling of the concentration of the greenhouse gas moves the emission pressure, or log of the emission pressure, down by log of 2 divided by 2. So for every doubling, all the wave numbers, nearly all the wave numbers, move down log of pressure by the same amount. And this is what a train does. When a train moves, all the cars move by the same amount. That's important. If this were not true, then some cars would move more than other cars, and the train becomes decoupled, or one part of the train smooshes into the other part of the train. It's just not how trains work. If the conductor rang the bell or tooted the horn, whatever, say all aboard, and then started moving, and it did this. Well, that's just not good, first of all. That's just not what trains do. So it's these two pieces of physics that tell us that for the 15 micron band, we can think about CO2 as this train of tau equals 1 levels. Okay, so if I start with a concentration of Q naught, the train looks like this. And in fact, for Earth's current concentration of CO2, the train corresponding to the tau equals 1 levels for CO2 has its tail in the surface and has its head up in the lower stratosphere. So it's a range just like depicted here. If I then double the concentration, let's say that doubling of concentration moves the train forward by 1 car length. Then there we go. Train moves forward 1 car length because of this log 2 divided by 2 thing that we talked about. If we double again, the train again moves forward by 1 car length, moving higher up into the atmosphere. Now, what's important to recognize here is that every time we double the concentration, we are effectively replacing a car at the surface with a car in the stratosphere. Yes, it's done by the train moving, but the end result is to take a car from the surface and move it into the stratosphere. So a car from the surface and put it into the stratosphere. Double again, I take a car from the surface and I move it into the stratosphere. And you can see what the effect is. You've taken a car that was emitting a lot of spectral flux to space, and you replaced it with a car in the stratosphere that's emitting a small amount of spectral flux to space. And so this is the radiative forcing you get from CO2. Another important thing to note is that because you're taking a surface car and replacing it with a stratospheric car, it doesn't matter what the temperature is in between the surface and the stratosphere. I could have a really bizarre looking temperature profile in the troposphere. And so in this case, if you look at the width of the spotlights here, you can see that I'm assuming a really odd temperature structure to the troposphere, one that gets really cold, about a quarter of the way up the troposphere, then becomes hot again, then becomes really cold again, then becomes warm, and then finally cold as you get to the stratosphere. Totally bizarre. It'd be convectively unstable, not something you'd be able to sustain for very long, but it's a perfectly fine atmosphere to think about for radiative forcing. And lapse rate theory would, be totally confused by this because it needs a single lapse rate for the troposphere. Of course, we saw that we don't even need a troposphere. So why is it that we don't need a troposphere, that we can do funny things to the temperature profiles? Because when we move the train forward, we effectively take a train car from the surface and move it to the stratosphere. It doesn't matter what's happening in between because we're not affecting how many train cars are in the troposphere. Okay, so that gives you an intuitive explanation. If we actually go through the math of it, we find that the forcing from a doubling of carbon dioxide is this expression here. We get pi times log of 2 divided by b times the difference in Planck distributions at the surface temperature and the stratospheric temperature. This b is simply the slope of this line. It's just one piece of physics we need from CO2. We need to know the slope of this kappa line. So kappa goes like e to the b wave number. Just need to know that b, and we can plop it into this formula for the forcing from a doubling. And if you put in numbers, you find that you get about 4 watts per square meter per doubling of CO2. Now, before I conclude here, let me just mention when this fails. And this will fail, this log scaling will fail if we move to concentrations that are too low or if we move to concentrations that are too high. Basically, it works for around 4 to 4,000 ppmv. If we go lower than 4 ppmv, then our train is backed all the way onto the surface because the concentration of CO2 in the atmosphere is so low that a lot of the tau equals 1 layers are buried in the surface. And so it's the surface itself emitting directly to space. Now, if I move the train forward, I'm not just taking a car from the surface and replacing it with a car in the stratosphere. Instead, I'm taking a car from the surface and replacing it with the car in the troposphere whose temperature is varying every time I double. And so I'm not getting that simple behavior. So the log scaling breaks at low concentrations. Similarly, it breaks at high concentrations because there are other bands of CO2 that start to become important. And those bands come along. It's like tacking additional train cars to the side of the existing train cars, which again, no train actually looks like that. And so you'd have this slug of stuff moving up through the troposphere, and the story becomes more complicated than, again, just taking a train car from the surface and replacing it with the train car in the stratosphere. And so you end up with a larger forcing because you have these other bands now starting to play an important role. Okay, so let me wrap up. This is my summary slide, everyone's favorite slide, because it means I'm done. So in summary here, we learn that we get the same forcing for every doubling of CO2 because of a couple simple reasons, or a few simple reasons. First, the tau equals 1 level of emission to space moves down the log of pressure axis, moves upwards in the atmosphere, by log of 2 divided by 2 for every doubling. So that tells us that all the train cars move at the same speed. And then we learned that the spectrum of CO2 is such that the wave numbers are distributed uniformly on an interval of log kappa, and therefore are distributed uniformly on an interval of log emission pressure. And this tells us that the train cars are hooked up to each other the way you'd expect, one after another, like in an actual train. Finally, for present day concentrations, the head of the train is up in the lower stratosphere, the tail is in the surface, and so when we move the train one car forward, we effectively replace a train car at the surface, 289 Kelvin, with the train car in the stratosphere, 205 Kelvin, and so we get a very simple expression for the forcing from the doubling, which is the size of the batch of the wave numbers that moves for every doubling of CO2, is that, log 2 over b, times the difference between pi b at the surface and the stratosphere. So that's the story, and I'll end there.